Soccer at 10:45. No, it's hard. What? No, like, I'm gonna get up at least initially. I want to get up all day. Oh, these questions.
I sure hope I'm that guy.
Does everybody have a syllabus? Raise your hand if you're okay.
Yeah, just think about it. Yeah, apparently it's like not.
I'd go like
Hey, Spencer. Stop off. Hey, we're actually. Hey, Spencer. We're actually not going to the Neptune after this. Oh, so you didn't buy that? Yeah, one of that. Oh, you were?
Okay, good afternoon. Does everybody have a syllabus? If you need a syllabus, come on down. So welcome to the NASA Research Seminar, Rocks and Stars. There's a little bit of information that I need to tell you before we start with our first speaker. The first one is, this is the last time you will get any handouts. The format of the course is such that each speaker will have about 3 to 4 questions that they will answer during the course of their talk. For today's talk, your questions are on page 2. On the last day of class, so May 31st, you will take a quiz that will be a subset of these questions. In order to get credit for this class, you need to get more than 50% of those questions right. So what you will need to do for each next week and each subsequent week is about Wednesday afternoon, I will post the questions on the course website. So the course website is listed at the top of this piece of paper I just handed out. You'll need to go there and download the questions. You'll notice that we have video cameras set up. We have live streaming if you do want to watch this remotely. If you do, we will be posting the slides for that at the time that the speaker is talking, but then I'll take them down immediately afterwards. So, let's see. Any questions? No? You can email me afterwards if you do have any questions. So I'm going to introduce our speaker. Our speaker today is Sarah Schmidt. She's a graduate student in the astronomy department, and she's only just a graduate student. She's getting ready to graduate in 2 months. She works with Professor Suzanne Hawley, and once she graduates, she'll be going to Ohio State to work on a postdoc. So, with that, Sarah.
All right. Can everyone hear me just fine in the back? Yeah? Cool. Okay. I don't like microphones in general. Okay, so my topic today is using large survey data to understand the smallest stars. But actually, I'm going to take a detour and give you an advertisement. Before I go to Ohio State this summer, I'm teaching a course. It's an astronomy elective on the solar neighborhood, understanding the universe within the nearest 50 light years. So if you're looking for a couple credits this summer, it's a 5-credit course, and you like what you see today, you can check out the information I post online or send me an email, chat with me after class. So back to the topic at hand, using large survey data to understand the smallest stars. Now, I'm actually going to get to the topic only in the last maybe 10 minutes of the talk. I have taught introductory astronomy a couple times, so I'm going to start off with a lot of material on how astronomers do science. I'm actually going to start out by answering the question, what are stars? Many of you probably know, maybe some of you don't. In particular, I'm going to talk about how we find stars, how we define them, what sort of properties we can measure. Next, I'm going to give you a couple reasons why small stars are interesting. I work in particular on the smallest stars. Then I'm going to talk about what are surveys. I talk about large survey data a lot. That's what I work on. And I'll talk to you about different sorts of them, what kinds are good for my science. Then I'll get into the real details, what we can learn about stars from surveys. So what are stars? Well, we'll start off with just looking at an image of the night sky taken by a telescope. First, all we thought is stars are points of light in the sky, and that's the image credit along the bottom. When we learn more about them, we realize that there's sort of 2 components to the definition of what is a star. So stars are gravitationally bound spheres of gas. That's one part of it. And the second part is that they're fusing in their core. So they could be fusing hydrogen to helium. A lot of them are. When stars get older, they fuse other things. So 2 basic definitions of a star. When we look at stars, we classify them by their mass. This is because the mass of the star determines all the other properties of the star. So if you know the mass of a star, you can find out everything else about it. The trick is that you can't measure the mass of the star really easily. You can't put a star on a scale. You can't push it and see how hard it is to move. You can't count the number of atoms in it because there are too many to count. So we have to look at secondary properties that the mass determines, like temperature and luminosity. So we find that more massive stars are hotter and brighter. So if stars have more mass, the mass of the star pulls it in, the gravitational force is greater, there's more energy in the core, fusion happens faster, more efficiently, and so it's brighter. It puts out more energy. On the converse, if a star is less massive, it's cooler. It doesn't have as much energy pushing in. It can't burn as fast in its core. So those stars are cooler and fainter. We can't measure temperature and luminosity, though, is the trick. Temperature, well, you imagine putting a thermometer in something or figuring out how much heat's there. What we can measure is color. Temperature relates to color because material of different temperatures emits different colors of light. So if your star is really hot, the material at the top of the star will be really energetic and moving very fast. It will emit really energetic light, blue light. If your star is cooler, the material's not moving as fast, emits lower energy stuff, that material is cooler, which is redder. Great, so we have temperature. Luminosity is almost trickier because luminosity is how much energy is that star putting out? How much is it emitting? Well, we can't actually know that by just looking at a star. What we get is our observed brightness. We get how bright it looks to us at Earth. I think of that as counting the photons. How many photons hit our detector? How much light can we detect? That tells us our observed brightness. But we also need distance to get how much light it's really putting out. I could do this with math, but it's also just easier maybe to think about dark night. You see a car that's really far away. As it moves towards you, the headlights get brighter, or they look brighter. The headlights aren't actually getting brighter, it's just that when light is closer to you, it looks brighter. So in order to figure out how much energy a star is putting out, how bright it really is, we need both its observed brightness and the distance. I'm actually not going to talk in detail about how we measure distance. Parallax is the method. It's sort of more of a tangent to this lecture, so you can ask me about it some other time. So here's a plot that astronomers use to classify a star by luminosity and temperature. Along the left side, it's a little bit cut off. It's on a log scale, the luminosity. So at the top is 10 to the 6th times the luminosity of the sun. Near the bottom is 10 to the negative 4 times the mass of the sun, times the luminosity of the sun. And if you're talking about stars on the main sequence, which is how we talk about stars that are burning hydrogen to helium, they fall on a sequence of luminosity and temperature, which depends on their mass. So as we get redder and cooler, we get less massive, smaller, and redder. Great. Why am I emphasizing this? Because when I talk about small stars, I want you to know they fall down here. They're not only small, but they're faint, they're red, they're less massive. And this plot actually doesn't show all of the objects I'm concerned with. We have to extend it because I don't only want to talk about stars, I want to talk about objects smaller than stars, or brown dwarfs. So a brown dwarf is an object that looks a lot like a star, and the first part of the definition I taught you for a star is correct. It is a gravitationally bound sphere of gas out in space. The difference is that brown dwarfs don't fuse in their core. They don't have enough mass to pull in their exterior to heat up their core to high enough temperatures that they can fuse. So basically, they're not big enough to fuse. They don't have what it takes. And brown dwarfs are really interesting because of this. Stars, it turns out, once they start burning, they don't change much. Brown dwarfs change as they age. And this is one way of showing this. These are some models that I pulled from a paper, and what it shows is the log of the luminosity, or the brightness of the star or brown dwarf, as a function of age. And that luminosity, again, is on a log scale. That negative 4 point corresponds to the negative 4 point here. So we're talking about the smallest stars and the largest brown dwarfs. Here's how you split them up. The brown dwarfs are on the bottom here, and the stars are on the top. So during this time, this 0 to 2 gigayears is the unit, billion years is what we use. Both the stars and the brown dwarfs are changing. Stars actually take a little while to form. They don't just ignite immediately as soon as they form. Brown dwarfs, they form and then they keep on cooling down. Their luminosity keeps on going down over time. So, and for some of these objects, if you're looking at object that falls on that -4 point, you know its luminosity, but you don't know whether or not it's fusing in its core. You would only know if you could tell how old it is. But age? How do you figure out the age of a star? You can't stick around and just see how long it's been here. Stars are millions to billions to trillions of years old, so we can't just wait. There are actually very few properties that we've found that even correlate with age. A star is kind of just a star, even whether it's been burning hydrogen and helium for 1 million years or 2 billion years or 6. So there are a few ways around this, and the one that I'm going to talk about today is actually velocity. So velocity relating to age doesn't seem very logical, but there's an explanation, of course. And the idea is that orbits around the galaxy become increasingly random over time. So all stars orbit the center of the galaxy, sort of like all planets orbit the sun, or all solar system planets do. So as they orbit, though, in the galaxy, there's a lot more stuff around them. And when a star goes by another star, that other star may pull on it gravitationally, which changes its orbit just a little bit. As stars age, they have more of these interactions. They get pulled out of their original orbit just a little bit more and a little bit more. So when you're looking at a star that has a really high velocity, it's probably an old star. And I'll talk about this actually a little bit more in more detail, but velocity may be one of the keys to telling the difference between stars and brown dwarfs. Right now, I'm going to move on to why are small stars interesting. I like them for a reason that I'm not actually explaining fully here. It's mostly just because I like the underdog. They're small, they're faint, they're in our neighborhood. But some reasons why other people think they're interesting, and I agree with, small stars, it says, are very common, it turns out. They're the most common thing in the universe. This is a graph that shows that. On the y-axis, we have number. It's sort of a log scale there. It's not, doesn't go up very logically. And on the x-axis here, we have different sorts of spectral type. That's basically a proxy for how blue or red or massive or not massive. So the massive stars are over by the A star, less massive stars are over here by the M dwarf. And this is the number within about 40 light years, I believe. So we have about 250 M dwarfs, or very small stars, within the same area. With all the other stars, we have about 50. So small stars are what the universe is made up of. They're very common. I said this is just nearby us, but it doesn't change as you go farther away. This is interesting because you can use small stars to sort of trace out the galaxy. Often we use stars to try to figure out what our galaxy is shaped like. We can't go and view what the Milky Way looks like from outside, so we have to take detailed observations of the stars around us. The better your samples are, the more stars you have, the better you can define the shape of the galaxy. Next, small stars live for a long time. I'm not kidding about a long time. This shows lifetime. It's a function of mass. The mass is in units of solar mass, so it's compared to the mass of the sun. The age of the universe is given by the top of that arrow, about 14 billion years. And so if we take a star that has the mass of the sun, right, I have to control over there, you trace it up, trace it over, you have an age of about 10 to the 10th years, or 10 billion years. So stars like the sun are supposed to live that long. Our sun is not that old. It's about 4.5 billion years. But it will live for longer than that. We take a star with a mass of 0.2 times the mass of the sun, trace it up, see what its lifetime is, and we get 1 trillion years. Turns out that because there's so little mass on the small stars, they don't burn very fast, I said, which is why they're faint. But they burn so slowly that even though there's not so much material to burn as there are on bigger stars, it just takes them forever, well, trillion years to get through it all. So why is this interesting? Well, these stars, they're still around no matter when they formed. They haven't gone away yet. So you can use these stars if you can figure out things about their composition, about their distribution, to probe the really early times in our galaxy and in our universe. But sadly, the properties of these stars are not very well determined. Another reason I like them, the underdog. They're fainter, so we have less observations of them. But also there are things about them that are more complicated. The less stars get like our sun, the less we usually know about them. So like I said, age is something that we don't know very well. Composition, so what sort of elements are in there. The spectra that we analyze for these small stars are really complex, so it's very hard to disentangle one element from the other. Mass, I did say that temperature and luminosity relate to mass, but the exact form of that relationship is much better known for stars like the sun than for small stars. Temperature. Again, I said it relates to color, but exactly how it relates to color isn't necessarily simple. If you've taken much physics or astronomy, you've probably heard of a thermal spectrum. That's great, except that for these very small stars, there are a lot of absorption lines in that spectrum, so many that it cuts away and you can't figure out where the thermal spectrum's peaked. I thought I had another property on there, but 4 will do. I think one of the most interesting things is one I've already mentioned, that we can't yet tell stars and brown dwarfs apart. So say we had 2 objects, is what I call them when I don't know whether they're a star or brown dwarf. You can actually have the same luminosity, the same temperature at the surface. The surface looks exactly the same way. But in the core of one, hydrogen is fusing to helium, and in the core of other, nothing is happening. All that matters to the outside of the star is how much energy is coming from the core. It doesn't care how that energy is generated. So if this brown dwarf started out very hot, then it could still be relatively hot, putting out lots of energy. The only difference, as I said, is that when it gets older, it will have less energy to put out. It will be dimmer, it will be fainter, it will be redder. But we can't wait around 1 billion years for that to happen. We need to find other ways to tell them apart. The last reason why small stars should be interesting is because some habitable planets could be found around them. So we already talked about how common they are. If planets could have life around these small stars, then life could be extremely common. So we need to figure that out. People used to think that you'd need a solar-type star to have a planet with life around it. But what we're finding out, and what people are doing more detailed models of than this, is that if all you require for there to be life on your planet is liquid water, then there's a zone around a star like the sun, which is over here. There's like a zone of distance from the star where that temperature would happen. If you look at a small star, which is way over on that side, that zone is just very much smaller. There's less heat coming out of the star, but if you're closer to it, you'll get enough heat to melt ice into water, which we think may be important for life. This really puts an emphasis back on how important it is to figure out the properties of these objects. When we find planets around stars, the only way we can find things out about the planets is by comparing their quantities to those of the star. If we don't really know very well what the compositions, what the masses are of these planets, of the stars, then we definitely won't know what they are for the planets. So these are some reasons why I think everybody should study small stars. So, moving on to what are astronomical surveys. This is sort of a data-focused portion of the talk, and telling you how we do real astronomy research. So an astronomical survey happens anytime we look at the sky with a telescope, but we're not really looking for anything specific. There are probably reasons why the survey was initiated. We think we may find X, Y, and Z, but the data is usually made available online. If you're looking at something else, you can access it. So astronomical surveys are extremely useful. And when I think about them, I characterize them in about 3 ways. The first is in wavelength. So when I say an astronomical survey data, I'm usually talking about pictures of the sky, or what we call photometry. But there's a large range of the spectrum that you can cover with a survey. So some surveys happen, so generally you take a picture in a very defined range of the spectrum, and you compare it to another range nearby so that you can get more information than just one picture. But you can do this kind of work in any wavelength. You can take a survey of the sky in microwave radiation. If you've heard of the cosmic microwave background, that's how they found that. You can survey the sky in ultraviolet, X-ray, infrared. There are just many different wavelengths. And you can't do them all at once because an X-ray telescope won't get you radio data or optical data. You need to have a separate telescope looking at most of these wavelengths to get any data at all. So the next main property is sky coverage. So we're talking about taking pictures of the sky. We've picked a wavelength. How much of the sky can we really feasibly take pictures of? And there's sort of 3 different approaches that I've seen that all work well for different things. There's taking pictures of the whole sky. Great. You can look at the entire sky. That's awesome. You can see everything. There's a hemisphere. So if you have to put your telescope on the Earth, you have to put it on one side or the other, so you can't see the whole sky at once. If you want to see the whole sky, you need a telescope in the northern hemisphere and the southern hemisphere. So sometimes surveys are limited by that. Otherwise, you may take what's called a pencil beam survey and just look at one portion of the sky and try to look at everything really detailed in that one pencil beam. Those are somewhat conversely related to depth, by which I mean, are we looking at bright things or faint things? To look at faint things with a telescope, you just need to leave the telescope at one point for a while, and you'll wait for enough light to come onto your detector that you can find each object. Faint surveys are often pencil beam surveys. You stare at one portion of the sky for a really, really long time. You can see very faint things very far away. But then if you want to try to do that for the whole sky, it would take 100 years or something. So there are very different ways you can go about taking a survey of the sky. So I'm going to give 2 examples of ones that I think are really interesting but bad for my science, and then I'll talk about the ones that are really good for what I work on. So if you're an astronomy buff, you've probably heard of this one specific optical survey that goes really faint and covers a pencil beam amount of space, and it's the Hubble Deep Field is what I'm talking about. So what happened was that the director of the Hubble telescope just had extra time. And he decided, we're just going to point the telescope at the same place for days. So light from galaxies and stars that are very, very faint, we were able to see it. And that's what this image is of. When you look really faint, sometimes you look out of the galaxy instead of in it. So a lot of these are fuzzy blobs, which are galaxies. So if you want to look at faraway galaxies, it's really good to look at faint light. Another example of a survey, which is not quite as popular but very different from the Hubble Deep Field, is an X-ray all-sky survey that's pretty bright wavelengths called ROSAT. And that's partially just to show what I think is a really interesting picture of the entire night sky, or the entire sky. So what you can see, that band down the middle, it's sort of a bluish thing. That's the plane of the Milky Way galaxy. And the diffuse blobs that cover most of it, that's hot gas that's expelled from supernova in the galaxy. And then you see bright points, and those are usually high energy sources. None of these are really stars. There are a couple stars that you can find in this ROSAT catalog if they're very strange ones. But mostly, you're looking at high energy sources and very hot things when you look in these X-rays. Okay, so probably enough about science that isn't mine, at least for me. When you're looking for small stars that are mostly nearby, you're looking in optical and infrared wavelengths. So that's where stars and small stars tend to have the most light. They're relatively cool, so infrared is a really good wavelength. And optical will help you find them as well. You want to go for an all-sky survey or maybe a hemisphere if you can't get the whole sky. Stars are all around us, and especially if you're looking right in our neighborhood, you're not looking far away enough that the density falls down. If you look out of the galaxy, you start to see less stars, but for stars this faint, that isn't going to happen. And the other one, I'm sort of cheating. I said that you probably can't do a faint survey and look at the whole sky. It would take too long. But I want to look at the faint objects in the sky. So what I really mean by faint is as faint as you can go. When you're looking at really small things, they're not going to have a lot of light, so the more you can get, the better. So optical or infrared, a lot of the sky, and as faint as you can go. 3 surveys that I'm going to talk about did a really good job of this, or are still doing it. That's WISE, 2MASS, and SDSS. I'll talk about them in a little more detail after I just put into perspective what wavelengths they have. So this is the same picture I showed you before of the entire electromagnetic spectrum. We're zooming in on the optical and infrared portions where we have visible, near-infrared, mid-infrared, and far-infrared light. So what I also wanted to point out here, and I didn't put in the graph that I meant to, visible and near-infrared light, you can see really well through the Earth's atmosphere. As you get into mid-infrared light, the Earth's atmosphere actually absorbs all that. So in order to get this light, and actually this light, you have to send something into space. So I'm going to talk about 2 missions on the ground and one in space. So SDSS up there, it's mostly in the visible light and has 5 different bands of coverage or filters that it took pictures of the sky in. The 2 micron all sky survey in the middle, it sort of covers the near infrared, and WISE hangs out in the mid infrared. Just to show you pretty pictures of these, this is the picture of the telescope that's used for the Sloan Digital Sky Survey. It's a 2.5 meter diameter mirror, and it's located in New Mexico. And some of the labs that UW is a big hand in running this. Some of the offices and labs that help with this telescope are actually located on campus. But that telescope's still running. It switched from taking pictures of the sky to taking spectra, which I'll talk about a little bit more later. For 2MASS, the prettiest picture that you can find about it, this is actually the entire sky in those 3 different near-infrared wavelengths. So what you can see, the plane of the galaxy in the middle looks sort of white. There's diffuse red-brown colored stuff. That's all dust. And down on my side here are the Large Magellanic Cloud and the Small Magellanic Cloud. This is actually a mosaic of all of the images that the survey took, and most of the light is just from points of light from stars. So 2MASS is valuable in that it covers the whole sky. SDSS, I showed you that the telescope is on the ground. It doesn't. 2MASS actually had 2 telescopes. They got the whole sky. The next one is the most recent and perhaps exciting mission, the Wide Field Infrared Sky Explorer. It's a NASA Explorer mission, which means that it's not a giant multi-year mission like the Hubble telescope. They just sent up a satellite which for 6 months took pictures of the entire sky in 4 infrared bands. And it actually finished that survey, I think, in December. I could be slightly off with that. So 3 surveys covering a large portion of the spectrum. I've talked to you about how we do that, but what can we learn about stars from surveys? And I'm going to focus in on 2 of the things that I work on in detail. There's plenty we can learn about surveys more than this, but here's what I think is most interesting. It's sad that you can't see the entire word of discovery, because that's going to just stay there for the next couple slides. So when I say discovering stars, what do I mean? Well, I've already said that we've taken pictures of the entire sky at many wavelengths. So how have we not found everything? Well, the trick is that here's a typical frame of data from the 2 micron all sky survey. This is about 1/10,000th of the whole sky. how many stars are there in there? I don't know, maybe 100 or 200. So no one has gone through and counted these by hand. Automated software has put information about every single source on the internet, so we have a catalog. But there's no way you could tell that this object, which the circle is around, is one of the most interesting objects in this frame, or at least according to me, it's a very low mass star. You can't tell that from looking, and when you look at the data and try to figure out which of these sources are interesting, it's not so easy. So how do we discover new stars? So first you need to have an idea of what you're looking for. So if you're looking for a star that's fainter than all the other stars, well, okay, it's probably less massive, it's probably redder. Oh, you should probably look in really far infrared or mid-infrared light. If you're looking for maybe a really distant galaxy, well, you want it to be really far away, so you want it to be very redshifted. You're also looking at red light. You just need to have a conception of what part of astronomy you're looking in. That usually means estimating the color and brightness, either because you want to find another object that's like this one you already found, or because you have an idea of where you can push the ones that you already know about to next. So then, once you have that, you select objects based on their color. So, to give you a hands-on example, oh no, I'm going to show wrong information in a second. This is actually from a paper that I didn't collaborate on this one, but I collaborated on a similar one. What I'm showing are two different graphs. Brightness is on the y-axis and color is on the x-axis. And that's actually wrong. Bluer stars are here and redder stars are here. And the y-axis is right, fainter's on the bottom and brighter's on the top. So the left panel shows objects that were found that the authors decided, okay, these black points are the ones that we want to find more like. Great. So draw a couple lines in how bright you think they should be and what color you think they should be, and then apply it to this right panel, which shows, I think it's approximately 1/1000th of the entire sky of data in the 2-micron all-sky survey. So in this particular example, 2 objects fall in that category. So we have 2 candidates for what we want to find, which are really small stars, smaller than those M dwarfs that I showed you before. Okay, we've got the color magnitude, but there's actually one more step, which is take spectroscopic data. Colors can fool you. Sometimes an object you'll take a picture of it, you'll try to figure out what color it is, and it won't tell you everything. It won't tell you enough. You won't know what it actually is until you take a spectrum. So just as an example of what a spectrum is, I'm showing you across the top there, it is an image of a spectrum. So you take light, you put it through a prism, you get a nice rainbow. The black portions are called absorption lines. So if something's stopping the light at that wavelength, you'll get an absorption line there. What's below that rainbow is a graph of intensity as a function of wavelength. It's if you took a line of that spectrum at the top and graphed how much light came at each specific wavelength. On top of it are shown a blue filter and a red filter. That shows you what you get when you take a picture. You take just a portion of that spectrum and you get one number for what may be actually a more complicated feature. Okay, so 3-step discovery process. You have your, you figure out what you're looking for, select on color, and then take spectroscopic data. This works really well. I've found, I think, 400 stars / brown dwarfs, not sure yet, using it, including this one. I'm showing this partially to show you the example of a spectrum of one of the smallest stars. We have flux or intensity or amount of light on the y-axis, wavelength or color on the x here, and this is what they look like. The really interesting thing about this is that if you just look at its color and magnitude, it looks like a star that's twice as big as it. it just has really weird colors. But when you look at this, it looks normal. So when I look at the spectrum, I actually think of this object. This is an artist's conception of an L dwarf, which is a class of objects that's the very small stars and the very largest brown dwarfs. So it's sort of like our ability to take a really actual picture and really figure out what things are, is to take a spectrum. The other example I wanted to show you is, so for a while people have theorized that there are these brown dwarfs that we haven't seen that are very cold, that are maybe as cold as, say, Jupiter. And everyone said, we're going to find these using the Y survey. We have figured out what their spectra are. We know what colors they're going to have. As soon as we get this data, we're going to find them. And they did. This is a spectrum of one of the coldest objects ever found in space that is not orbiting another object. So it's not a planet because it's not around something else. It's very cold. A Y dwarf. And I'll show you an artist's conception as well. It's very faint, and we often color things purple when we know that they're fainter than what the red ones are. Okay, so discovering objects, really interesting work you can do with surveys. But once you've found the objects, what do you want to do with them? Well, sometimes you just want to count them. You want to know how common they are. That's how we know there are a lot of M dwarfs. But I mentioned this before, and one of the things that I'm really interested in are ages, which I probe using velocity. So I talked about velocity and how it's useful a little bit, but I didn't talk about how you can measure it. Velocity has two components, or three components, but we can measure it in two ways. When you see something that's really far away and you know it's moving, well, you can see it moving both on the plane of the sky and back and forth from where you're standing. So one of the ways we measure velocity is using something called proper motion. So what I'm showing is this, most of the background of the picture hasn't changed over the course of 16 years from 1991 to 2007. But this is an image of a single star that's moved over the course of those 16 years. Most stars do move over the course of 16 years. You just sometimes can't see it. It just looks like it hasn't moved that much or at all. This is actually the star with the highest proper motion or highest apparent motion as we see it. The three surveys I talked about are actually ideal for figuring out proper motions because they're separated in time. This is for a sample of stars and brown dwarfs that I'm working with. This is a number of observations, so the number of stars that were taken by each survey. So like when this picture was taken of that particular star as a function of year. So the 2-mass survey that I talked about, it's actually sort of an old survey. It started in 1997, ended in 2001. When you compare that data to data from the WISE survey, which I said just happened a year or two ago, it must have not stopped in December if it's 2010. They only recently let us look at the data. Anyway, so the separation years means that we can detect even small motions in proper motion and calculate velocities from them. The other component of velocity is radial velocity, which you can measure using the Doppler shift. And this is a kind of dopey illustration I found online that shows that as a star is moving towards you, the light it emits is shifted bluer. And as it moves away, the light is shifted redder. You can measure that shift and calculate how fast an object is moving. All you need is a spectrum to look at. So you can measure the velocities. When you do, you get a plot that looks like this. I'll explain it. This shows number of objects as a function of velocity. And these are roughly Gaussian distributions, so sort of a normal distribution. And the reason I'm showing two is because younger objects have a narrower distribution. I talked about how objects, as they orbit the galaxy, they continually interact with more and more things, make their velocities increasingly random. So older objects have a wider dispersion. So you can't just say, oh, that star is moving fast, it must be old, or that star's moving slow, it must be young. You have to take a group of objects that you think have similar properties and look at their distribution of velocities to get an age. That's why velocity and age are not exactly easily related. When I do this for my collection of really small stars and brown dwarfs, I get this plot, which actually takes some explaining. So what I've done is I've taken a color in the near infrared. I've compared the light at one wavelength to another, and then I've grouped the objects based on how blue or red they are. So I took a group of blue objects, I took a group of normal objects, and a group of red objects, and objects that are a little in between, measured their velocity dispersions. That's what I'm showing on the y-axis. Larger dispersion, I said, is older, and a smaller dispersion is younger. So what I found by using velocities is that for these objects, this particular color tells us something about their age. We hadn't been able to see that for individual objects, partially just because we couldn't measure their ages. So that's one of the things you can do with a large sample of objects from a survey. The last thing I'm going to talk about is bring it back to stars versus brown dwarfs, this graph again, where we separate the brown dwarfs and the stars. So one thing you might think you can figure out is that, say you take you take a group of objects, not stars, maybe stars, at one luminosity, and they should have a certain number of brown dwarfs and a certain number of stars. You go fainter, there should be more brown dwarfs. You expect them to be younger. So you might think, okay, if I take warmer objects, take their velocity, they might be younger than if you take objects that are more likely to be stars, they would have a wider velocity dispersion than objects that are more likely to be brown dwarfs at a similar brightness. So you might expect a trend in velocity dispersion with I'm showing spectral type, but it's basically smaller redder to this side. But we see no trend. When you look at the velocities of these objects, you find that the stars and the brown dwarfs seem to be the same age. So maybe we can't use age to distinguish brown dwarfs from stars, but maybe we can. This is actually stuff that I'm currently working on, and if I gave this talk in a week or two, I might have a better way of showing this. So, hopefully we'll find a way to get ages from velocities for stars versus brown dwarfs. So I'm going to wrap it up, and I wanted to give you two take-home points. One is that the properties of stars, especially small ones, can be difficult to determine. So when I used to think about astronomy before I worked on being an astronomer was that, we must know everything about the stars. We can take pictures of them. Isn't that enough? It's really not. We need to learn more. And that most astronomical objects are discovered through data from large surveys. That's sort of the way that we do our work. If you're looking for new things, you have to look at a large list of objects. And that's actually all. You are totally right. I changed that last minute.
Okay. And then color, is that the other one, sort of?
Color, I think, yeah.
Okay.
I'll talk with her about it as well, but
Okay.
I actually had a whole other section that I took out last minute because my talk was running long.
Okay.
I just barely finished in time before I know what I was supposed to do.
Okay.
So.